Here we're going to consider the electrolysis of a salt solution. The only salt solution we're going to consider here is sodium chloride, and we're going to do it under two conditions. One where we have a low concentration of sodium chloride, and the other where we have a high concentration of sodium chloride. Let's first set up the system we're going to look at. We'll have a beaker, and in this beaker we'll have some water, an aqueous solution, and we'll add sodium chloride to that, which will dissociate into aqueous sodium ions and chloride ions. And here we'll hook up electrolysis system. So here will be electrode, here will be electrode. They'll be going into the solution, and this will connect to a battery. And let's make this the negative terminal of the battery and make this the positive terminal of the battery. For the previous YouTube video about electrolysis of water, we said that electrons flow from the negative terminal of the battery to the positive terminal of the battery. If you're an electrical engineer, actually the current is seen to flow the opposite direction, but as chemists we're interested in where electrons go, and so they'll go from the negative terminal to the positive terminal. Okay, where the electrons are going here, this is called the cathode, and the cathode is where reduction occurs. So reduction, these electrons will go on some atom and reduce its oxidation number. Over here on the other side is the anode, and that's where oxidation occurs. So I want to ask the question for this particular setup, what will be produced at the anode and what will be produced at the cathode? We have two possibilities here. Let's look at, say, the anode first. We have sodium. That can be oxidized? Probably not. Sodium is a +1 oxidation state. Really can't go to a +2 oxidation state. Chloride, on the other hand, can be oxidized. That is a -1 state. It can go to the 0 state and make chlorine gas. So that's one possibility at the anode, to oxidize chloride to chlorine gas. And we know by the previous YouTube video that we can oxidize water. We can take the O oxygen, which has a -2 oxidation state, and oxidize that and make it into O2 gas. On the reduction side, over here in the cathode, we can take sodium ions, reduce that from a +1 to a 0, make metallic sodium. We can also take hydrogen, which is in a +1 oxidation state, reduce that to a 0 oxidation state, and make H2 gas. All right, so those are possibilities. We want to know which will occur at the anode and which at the cathode. Let's take the cathode first, where reduction occurs. So we said that we have two possibilities. We have sodium will take an electron and make metallic sodium, which of course then would react with the water. And we can also reduce water. Let's write it this way. We're going to make H2O. And, well, we'll put so many electrons on there. What we're going to reduce is the hydrogen +1 oxidation state to make H2 gas. And then we'll make some OH over here. And to balance this, let's put a 2 in front of here. We'll then have 2 electrons, 1 electron from each hydrogen H+ to make H2 gas, and we'll put a 2 here to balance. Now let's write down the E0 for this. And remember, the 0 means standard state, and the E0 means reduction potential. So let's look at the reduction potential for sodium. We'll go, well, we can go in Tro, but in fact, let's go to Wikipedia. Here's the Wikipedia page that has all those reduction potentials. And sodium really doesn't want to be reduced. It wants to get rid of the electrons, so it's probably down here. Sodium, well, let's see, sodium, where is it? Oh, looks like Wikipedia lists some negative to positive. Different from Tro. Okay, so where are we here? Sodium Na+, that will be, oh, guess a little bit down further. Oh, there it is. Sodium right here. Sodium being reduced to sodium metal. the standard reduction potential for that is minus 2.71. And if you looked at the YouTube video of electrolysis of water, we'll know that the cell voltage here, not standard state, but the cell voltage here is minus 0.41 because the hydroxide ion concentration in pure water is not 1 molar in the standard state, but in fact it's 10 to the minus 7th molar. So those are our two candidates, and we're going to ask which one will be preferentially reduced at the cathode. The one that's preferentially reduced at the cathode is the one that has the higher reduction potential. This looks like it has a higher reduction potential. It's less of a negative number. So at the cathode, what will appear will be H2. We will not make metallic sodium. So this will appear, and over here we'll have little bubbles of gas coming up when we connect the battery. We're sticking electrons on the H for H2O, make H2 gas. H2 gas will be produced here. Now let's look at what happens at the anode. And again, anode is where oxidation occurs. And we said again we had two possibilities. One is that we can oxidize a chloride, Cl minus, go to Cl2 gas, and let's put a 2 here to balance it, and there'll be 2 electrons coming off, and the oxidation, so there's the half reaction for that possibility. We also said that we can take water and reduce the oxygen, which is in a -2 state, and make that into O2 gas. And we'll make H plus here, and let's put a 2 here to balance that. We'll have 4 here, and that'll take 4 electrons, or that'll produce 4 electrons when we oxidize the oxygen. All right, let's go back and see what the standard cell potentials are. Let's see, chloride. We'll give that a gander here. Again, Wikipedia, in contrast to Tro, Wikipedia starts with the -1s and go positive. So let's see, where would that be? Probably down here somewhere. So we're looking for chloride being reduced, or chlorine gas being made. Oh, there it is. Okay, so again, these are reduction potential tables, so we write it as a reduction, but in fact we're taking chloride and going back. So if you really rewrite this, this would be -1.36, but following Tro, we're going to keep this as a reduction potential. All right, so plus 1.36 for this reduction. We'll just write that here. Again, these are E zeros. We said what's 1.36. And then from the YouTube video on electrolysis of water, the oxidation potential here is 0.82, and these are all in volts. All right, so let's take a look here. This looks like it preferentially will be reduced because it has a higher reduction potential. So this means that this will be and this is not as easily reduced because it has a lower reduction potential. However, when you talk about oxidation, which is there, you have to switch your logic. So the one that has the lower reduction potential has the higher oxidation potential. So what you would predict in this case is that this has the lower reduction potential or the higher oxidation potential. You would predict that this would appear, O2 gas would appear at the anode. So if we go back to our setup, our logic says that H2 gas will appear at the cathode, and O2 gas will appear here, and the sodium and chloride won't be affected. In fact, what we're doing, if we just have a sodium chloride solution, what we're doing is just oxidizing water. The sodium and the chloride doesn't really care. And then if you do this experiment at a low concentration of sodium chloride, indeed what you find is that H2 is produced at the cathode, and O2 is produced at the anode. All right, so far so good. Now let's do the same experiment where we have a high concentration of sodium chloride. Here we have a high concentration of sodium chloride instead of low, high being like 1 molar instead of like 10 millimolar. All right, at high, and you do the experiment, we're not going to calculate this. At high concentration of sodium chloride, what you find is that, oh yeah, still H2 is produced at the cathode, but guess what? Cl, this is Cl2, chlorine gas, is produced at the anode. So here we predict that O2, based on reduction potentials, O2 would be produced at the anode, but in fact you do the experiment at high sodium chloride concentration, you find, oh my goodness, Cl2 is being produced. So typically what you do is you make up some sort of name for the fact that what you predicted didn't happen, and what is made up, the name for this phenomenon is called overvoltage. Overvoltage. Overvoltage means, if we go back here, that, oh, really it must be that the reduction potential of water to produce O2 is not really less than the reduction potential of chloride. In fact, it's greater than. So it's not 0.82, it's greater than 0.82. In fact, it's greater than this. And so therefore, what happens, because you did the experiment and not what you predicted, oh, therefore there must be a bigger reduction potential than you thought here. And a bigger reduction potential than you thought here is called, oh, that must be overvoltage. And if you take a advanced chemistry course and well, you take instrumental analysis, for example, or something like that, what you'll find giving various explanations for that. Here's your electrode sitting in your water. And then you have to have water come up here, and there's a diffusion, and there's a diffusion barrier, and blah, 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 blah. So chemists have made up explanations for why you have this overvoltage phenomenon. But basically, you do the experiment, and at high concentration, you produce chlorine gas instead of oxygen. H2 and O2 are produced at low sodium chloride concentration. It is as if you didn't have sodium chloride present there. All right, so there's the dirty laundry of chemistry.